With this extended notion of environments, then let's look at how our type checking rules will change. So it used to be a lambda of some name having a type. With the body expression, we would just check the body expression with an extension in the environment. But now we need to make sure that that tal1 that's explicitly listed after the variable is okay. So that's where we use our typecheck operation. Right? And when we put this into Plait code, then we have a lam e expression that we're type checking. This arg type is the one that was declared, so we're going to call typecheck on that arg type. Right? And as long as that's okay, then we go do our old usual thing of creating an arrow t with the declared argument type and type checking the body in an extended type environment. If we look at the let type form, now here's how let type should work. It says I'm going to type check the body e here, so that's the last part here. Type checking the body e, which will have a tal0, and that'll be the type of the overall let type expression. All the work is in setting up the right environment to use in type checking e, and that's tal prime. Tal prime is defined as gamma prime rather. Gamma prime is defined as whatever our current gamma environment is, with that information about the type declaration d. So d has variants x1 and x2, where the field types are tal1 and tal2. We put that in the environment, but also x1 and x2 can be used like functions in the body of e. They're constructors and they construct variants, but they have the same type as functions. And so we put that in the environment also. We say x1, if you use x1 directly, it has type tal1 arrow d. Give me a field value, I will give you an overall variant of type d. And x2 is very similar. There's some redundancy in the environment at this point because this information is already covered here, but it turns out to be simpler to duplicate it in the form that we already expect to see function types. For type case, we have a type d here and an expression that should be of that type. So we write that directly right here. And then we have two variants, x1 and x2, and we need to make sure that x1 and x2 are declared to be the types for d1. And in this notation, we write it this way. We say gamma must be some environment that maps d to exactly those two tags, x1 and x2. And when we find that information in the environment, it also gives us tal1 and tal2, so that in this first case, e1, we know that e1 is able to refer to the variable x3, and it has type tal1, which came right out of the environment for the x1 variant. And e2 is similar, with the type x4, variable x4, mapped to the type tal2 out of the environment. Both e2 and e1 then, they must have a type, and the types must be the same. They must be tal0. It turns out this let type rule is not quite right. There's a subtle problem here, but we'll defer that for just a little while. Turning that into code, it looks like this. So here we've got let type. Let's consider this example. Fruit, apple, and banana of apple 10. So the type name here is fruit. We've got tag 1 is apple, tag 2 is banana, and body is the apple 10. So in the end, we're type checking body. We're doing that in an extended environment. This looks very similar to the interp, but it's at the type level because we need to bind tag 1 as a function type. That is an arrow type going from type 1, which is like number, right, the type that we've declared for the field, to defined t type name. Because type name is fruit, right, that is the type that we're declaring right now. So we put those into the type environment, but also we need to put the information about fruit into the type environment. So that's why we're adding those to new tm, which new tm starts out by extending the type environment with this type definition. This is where we record the fact that fruit has tags apple and banana, and the field types that go with those are type 1 and tag 2. We put that in the environment, and we use that environment as we make sure that the declared types over here are okay. And it's important that we use this extended environment because when we want to make lists, then we want to refer back to the list type there. So it's recursive in a similar sense to letrec, only without some of the complexity because everything is declared explicitly. So we just make sure those types are okay, and if they are, then we type check the body. In the type case part, there's more moving parts again. So let's consider type case in this example. We need to type check this apple 10 form and make sure it is that declared type there. So that's what we're doing here. We're type checking the test expression, apple 10 for example, and making sure that we get a defined t back where that name in the defined t matches the type name that was declared in the type case. Okay. And then we'll need to do more things, but we need to make sure that this type name in fact made sense in the first place, this fruit here. So that's what we're doing here. With defined type lookup, we're looking in the environment for fruit and hoping to get a type def back. If we get a type def back, then everything is okay. If we don't, if fruit is not defined, then defined type lookup will raise an error. And we use that type def information when we want to type check the expression on the right hand side. So when we're type checking A here, we need to use the type of A added to the environment. So that is the t bind here added to the type environment. The A gets mapped to the type that corresponds to the first variant in the type definition, and so on. We type check both of these right-hand sides, and of course we need to make sure that they're the same type. And when we fill that in and add in the error checking, this is what the complete implementation looks like. We do have an extra helper function, tvarCheck. That's the one that makes sure that a type is well formed with respect to a given environment. Numt's and boolt's, they're always fine, so we succeed with no values. An arrow t is fine as long as the argument and result types are fine. And defined t, that's the interesting one. This defined t identifier, like fruit, makes sense if we can find a declaration for that type in the type environment.